Hello, everybody. I'm Gil Kalai, talking to you from Israel, and it is a pleasure for me to introduce Mathias Schacht. Mathias Schacht has made profound contributions to extremal combinatorics and to probabilistic combinatorics, and especially to the study of graphs and hypergraphs. He made a groundbreaking contribution regarding both extremal properties of hypergraphs, study of random hypergraphs, and a theory that combine extremal properties for random graphs and hypergraphs related to the so-called KLR conjecture. Mathias was educated in Germany, and he did his PhD work in Emory University. His work then was on the very famous regularity theorem for hypergraphs. In 2006, he received the Richard Rado Prize for this work, and in 2019, he received the Polya Prize for this work. Let me now give the floor to Mathias, and he will talk about restricted extremal problems in hypergraphs. Mathias, please.
Thank you very much, Gil, for this nice introduction, and thanks a lot to the organizing committee for giving me the chance to present some of my favorite research problems here. So I will talk about extremal problems in hypergraphs, and this area is connected with many great Hungarian mathematicians, and in particular with the three which I put up here as a picture. In the middle you see Paul Turan. Kind of many of the parameters in the field are named after him, as we will see in a couple of minutes. And he is surrounded by Paul Erdos and Mathias Schacht, which motivated some of the questions I want to talk about. So let's get started. So I would like to give a short introduction to extremal problems for graphs. And this is usually attributed to the Turán-type questions. And the way it was, or I learned about it, that somehow there were some earlier results. And in particular, there was one earlier result due to Erdós from the 1930s of the last century, where he kind of missed to ask the general question. So maybe if he would have asked the general question there, then maybe it would be Erdős theory, or who knows what would have happened. But anyway, so let me here just show a picture of his paper. So this is a paper which appeared in as a technical report at the Math Institute in Tomsk. And it's about some question about products of integers. And in that paper, he kind of used an argument, which he then summed up as follows. So what this really is about, it's about a graph theoretic question, how many edges a graph on 2k vertices can have without having a 4-cycle. And he observed in that paper that this can be at most of the order k to the 3/2, which is best possible. Anyway, so this was just a particular result, a lemma which he used in order to prove this arithmetic flavored question. And so, of course, as a graph theorist, you may wonder why you only consider such a problem for 4 cycles. It's kind of very natural to ask how many edges you need in order to guarantee some given subgraph. And this is precisely what leads to the following parameters. So for a graph f and an integer n, we denote by x and f the extremal number, which is just the maximum number of edges a graph on n vertices can have without having a subgraph isomorphic to f. So here I'm just interested in the normal subgraph containment, so we don't worry about whether it's induced or not induced. It's just a regular subgraph. And this parameter can be a little bit tricky. In particular, there can be easily some divisibility issues of n and the number of vertices of f. So a somewhat more robust and simpler parameter is the so-called Turan density, or what we now call the Turan density pi of f. If we scale this parameter by the maximum number of edges a graph on n vertices can have, so we divide it by n choose 2, and it's not hard to show that this limit, in fact, exists when n tends to infinity, because the sequence is monotone. And in particular, Turan not only determined this parameter, what we now call the Turan density, he in fact determined the extremal function for cliques. And so this was maybe the first general result in the area. And that's why many of the results or parameters are attributed to his name. And so what Turan showed is that this number of edges is maximized for the complete t-1 partite graph. So if you're interested for f being the clique on t vertices, then if we take the complete t-1 partite graph with balanced vertex classes, then this graph is the unique graph which has the maximum number of edges and doesn't contain a clique on t vertices. And this is the result of Turan from the 1940s. And this was later generalized by Erdos and Sós, and in the following form it was first posed by Erdós and Sós, that the Turan density can be expressed in terms of the chromatic number of the graph. Chromatic number is kind of one of the most natural graph parameters, which already appeared in the talk of Alex Scott. Just the number of colors you need to color the vertices of a graph, so that endpoints of different endpoints of an edge get different colors. And so we can express this Turan density in terms of the chromatic number by the formula which you see here. And this means in particular that we can avoid this limiting procedure, and we can really calculate or compute the Turan density. And also it's kind of interesting because it shows that these extremal examples, which were already discovered by Turan, are the optimal or close to optimal structures for any graph f if you just scale it by the chromatic number. In particular, this tells us a lot. So for example, it tells us how all possible Turan densities look like. They can only be 0, 1/2, 2/3, and all these numbers which you see here. Okay, so that's kind of, in some sense, a fairly satisfying answer for the graph case and resolves the graph case for determining these Turan densities. And so the next natural question might be, what about the hypergraph case? And in fact, Turan already asked this in his original paper. So here we consider uniform hypergraphs. That means we have, in this talk, a finite set of vertices V, and the edges now are k-element subsets of the vertices. And for most of this talk, k will be equal to 3. So here you see an example of such a hypergraph. Kind of there's a vertex set, and here's, for example, one edge and a couple more edges. And yeah, so these pictures quickly get a little bit messy. So maybe not too helpful, but yeah, so this is how these hypergraphs look. Okay, and for these objects, you can easily define the same parameters. So the maximum number of hyperedges a hypergraph on n vertices can have if it doesn't contain f. And you can scale it to the density. The only difference is now you have to divide by n choose k instead of n choose 2 in the graph case. However, somehow we are far away to have a similar elegant description of this parameter, of this Turan density for hypergraphs. And there are only few results known, or general results known. One is due to Erdős from 1964. He characterized all those for which just positive density is sufficient to be enforced. And these are the ones which are k-partite, which just means you can split its vertex set into k classes, and an hyperedge has one vertex from each class. So these hypergraphs have Turan density 0. And maybe for a famous or prominent result for an interesting hypergraph f for which a lot is known, I just here picked one example, which is the so-called Fano plane. So if you, this is just a projective geometry of dimension 2, where you have 7 vertices and you have 7 lines, and the lines are the 3 uniform hyperedges. And there it was conjectured by Mathias Schacht that the extremal construction is given by what you can say a complete bipartite 3 uniform triple system, where you split the vertex set into 2 sets of size n/2, and you include all the triplets which have at least 1 vertex on each of the sides. So those hypergraphs are it can easily be checked that the Fano plane cannot be embedded in this one, and obviously it has density 3/4, because basically on each side you have you lose 1/8 of the density. And the Kahn and Szemerédi in 2000 proved this result, which you see on the left, that this example is the extremal example for the Fano plane, and that the Turan density is in fact 3/4. However, they only proved, I mean, they didn't precisely prove what I just said. They just proved that the Turan density is 3/4, so that the extremal example is in fact this complete, what I call bipartite 3 uniform triple system. This was proved for large n by Szemerédi and Szymonowic, and independently by Kivash and Sudakov in 2005. And very recently, Raya and Bellman proved it for all n larger than 8. So maybe something somewhat interestingly, for n equal to 7, there are 2 extremal constructions, but yeah, maybe that's a little bit too much knowledge. Anyway, so this is an example where a lot is known. However, of course, there are maybe much simpler triple systems which come to mind, and why didn't I talk about those? Because unfortunately, much less is known about those. So maybe if you start to play around with 3 uniform hypergraphs, maybe the easiest examples where these extremal questions make sense or kind of are non-trivial is the one when you have 4 vertices, and on these 4 vertices you have 3 triplets. So here you see the 4 vertices, and this is 1 triplet, and this is the other one, and this is the last one. So the upper right corner triangle is missing here. And yeah, so this is kind of fairly simple object, you would think. However, here, even the Turan density is not known. So there's an extremal construction, which is believed to be optimal, which is due to Frankel and Szemerédi from the 80s, which gives 2 sevens, and it's kind of interesting because it has some iterated nature. And with computer methods, using the flag algebra introduced by Rasborov, Barber and Talbot currently have the best known upper bound, which is a little bit above the conjectured extremal density. The other, maybe even more famous example is the so-called K43 or tetrahedron. So now all 4 triplets on 4 vertices are present, or we want them to be present. And there was a famous construction due to Turan from the 40s, which shows that this Turan density is at least 5/9. And again, using computers together with flag algebra framework of Rasborov, one can get currently the best known upper bound is 0.56. Anyhow, so what we do, so if a problem is too hard, we try to kind of approach it in different ways. So one way is, of course, apparently we already gave up on solving it completely, right? For any hypergraph, 3 uniform hypergraph F is already, for so simple examples, we are currently not able to solve it. And then the second thing, of course, we can do is we can restrict the domain of the host hypergraphs for which we try to analyze this function. And this is the approach we have taken, and that's what I want to talk about next. So I will talk about uniformly dense hypergraphs. So roughly speaking, what we will do is we restrict the hypergraphs H, which we are interested in which we want to find a copy of the fixed hypergraph F, right? So H is large, F is fixed, and we don't maximize the number of edges over all hypergraphs H, but just those which have some additional assumptions. And this additional assumption will be that they have some natural distribution of the edges. And yeah, if you have I will make this more precise in the next couple of minutes. But if we have such a notion of an extremal function, then of course we can scale it and define some uniformly dense Turan density as well. Obviously, by definition, we have this monotonicity because we maximize over a smaller set. And in my talk, I will try to present several of these uniform dense notions if time allows. Okay. So before we talk about uniformly dense hypergraphs, maybe let's go back and try to define such a notion for graphs. And there's a well-known concept. We say a graph is bidense with density p, and there's some error parameter epsilon. But basically, for any two subsets of the vertices u and w, we have a p proportion of the edges between them. So if you imagine u and w to be disjoint, then of course there could be u times w many edges in between, and we want a p proportion of them to be present. If u and w are not disjoint, then we just count those in the intersection twice, or I mean, the way you should think about it is that we count the ordered pairs u, w, which are an edge in the graph, and then this formula is kind of just the expectation. And of course, if I want to have such a property for all subsets u and w, you could just take to be one vertex u and one vertex w, and then I would be forced to have the complete graph, which would be the only one which satisfies this assumption. So I need this error parameter, which kind of prevents such a trivial example. And basically what it says that we can only consider sets u and w up to linear size. For smaller sets, this definition is meaningless. Okay, and then yeah, as we outlined on the slide before in general for hypergraphs, we could define this Turan density, which then is the maximum density for which there exist bidense graphs which don't contain a copy of F, right? Or if you want to say it positively, it's the smallest density which guarantees you that every bidense graph of this density contains a copy of F. However, as it turns out, this parameter is kind of fairly easy to calculate because it's 0 for any graph F. And that's why this notion of bidense graphs kind of is very popular in extremal graph theory. For example, this is the notion essentially which wants to be, which we want to realize by applications of Szemerédi's regularity lemma, because it allows us to embed any fixed graph, kind of. So if a graph is bidense, then with some positive density p, then it contains any fixed graph F. And actually, even in the right abundantly, we have many such copies. Okay, so that kind of is what we can say about graphs. However, as it turns out, if we define such the straightforward generalization of this notion for a triple system, then the parameter becomes more interesting, and that's what I will tell you in the next couple of minutes. So we will say kind of define the straightforward generalization of this bidense concept for graphs, and of course, maybe one should call it tridense, but for maybe some historical reasons, we call it weakly dense. We say a triple system is weakly dense if whenever you take three sets, X, Y, and Z, the triplets going across these three sets, and which are hyperedges, is at least p proportion of all triplets. So here's just kind of some picture of it. So you have a hypergraph H, it has a bunch of edges, and now you take three subsets, X, Y, and Z, and you count only those edges, and you want that the p proportion of all possible triplets of this form are an edge. And this is kind of the natural generalization. And for that, we then define the Turan density precisely the same way as we just did it a couple minutes ago for graphs. For this parameter, we chose kind of the symbol of the three dots because each of the dots represents in some sense one of the vertex sets, which you can take as a witness for which you can check the density, X, Y, or Z. Okay. Now, in order to convince you that this is a natural concept to consider, or a more interesting concept to consider for hypergraphs, we should first find some weakly dense hypergraphs which don't contain all fixed hypergraphs F. So we should find a hypergraph F for which we would know that this Turan density is not again just 0 as it was in the graph case. And there's a construction which goes back to the work of Erdos and Sós from the 70s, where you just consider a random tournament. So we want to define a triple system, but in order to define it, we will first start with something, defining something on the pairs, and that kind of will be the key feature actually of this construction. So we take the vertex set V, and for every pair of vertices, we choose independently with probability 1/2 one of the orientations. And now we can look at the triples, and for the triples, we have to decide whether a triple should be a hyperedge or not of the hypergraph which we want to define. And we take all those triples which correspond to cyclically oriented triangles in this tournament. Of course, such a triangle appears in one direction with probability 1/8 and the other direction with probability 1/8. So they appear with probability 1/4, and it's not hard to show that if we define the hypergraph that way, so on top of the cyclically oriented triangles, then this hypergraph is weakly dense with probability 1/4. And so Turán-type estimates easily show that we can take any three subsets, X, Y, and Z, and everywhere we have density 1/4. Okay, so this is the construction of a hypergraph which will be weakly 1/4 dense. And as it was already observed by Erdos and Sós, any such hypergraph, no matter whether you do the construction randomly or not, you can take any starting tournament. Any such hypergraphs will not have 3 edges on 4 vertices, 3 triplets on 4 vertices. And the simple reason is like this. So if you want to have 4 vertices and you want to have the 3 triplets, basically in order to have 2 triplets, you have to start with a picture like this. Right, so maybe you can flip the arrows, or maybe you can kind of a little bit rotate it, but that's all you can do. So this is how it has to look. And now you already see if you want to include a third triplet, then there's no way to do it because the 2 vertices, which one of them it would have to include, is already a sink and a source. So that's impossible to involve into a cyclically oriented triangle. And that means on 4 vertices, such a hypergraph can only have 2 edges, and in particular, it cannot contain such a K for 3-. Okay, and that kind of is maybe one justification for studying extremal problems for weakly dense hypergraphs, because now the question becomes, so is this construction optimal, or is this density at least optimal, in the sense that if you are weakly dense with density strictly larger than 1/4, then you cannot avoid the K for 3-. And this was conjectured to be the case by Erdos and Sós in the 80s, and it was proved a few years ago by Glebov, Kral, and Wollitz using the Fleck algebra method. And I would like to, 2 things I would like to point out here. So one thing is, if you think about these weakly dense hypergraphs, and maybe you have never seen them before. So basically what we want some uniform edge distribution of the triples. And one naive idea could be, okay, so if I have a uniform edge distribution of the triples, maybe if I look at the link of a vertex, which are the pairs which complete this vertex to a triple, maybe this graph also enjoys some uniform edge distribution. But as we see in this example, if you look at it, all the link graphs here are bipartite. So they don't have this uniform edge distribution, and kind of this is just a very much naive thought, right? So they're not uniformly dense itself, and that's actually one of the problems. Another open problem, which is closely related to the construction, so I cannot avoid to mention it, is the following, which goes back to Erdos and Sós, which says basically this example has a property, it has just globally, don't worry about weakly dense, just globally density 1/4, and every vertex has a bipartite link. And they conjectured that 1/4 is the maximum. So if the density of a hypergraph, of a 3 uniform hypergraph, is a little bit larger than 1/4, then there should be some vertex which has a non-bipartite link. So in particular, it should have some vertex should have an odd cycle in its link. And this is kind of, I think, a very nice open question, because I think it encapsulates a little bit what is really something which we really don't understand at this point. And that's kind of, if you describe a hypergraph by a link property of the vertices, how these links interact. Because if I just want to have the link of one vertex to be bipartite, I could imagine that I could put there a complete bipartite graph of density 1/2, and then the whole hypergraph would have density 1/2 if I could kind of arrange it for all vertices this way simultaneously. But somehow this interaction of these links kind of forces the density apparently to be smaller. And kind of, so I think if we would understand this problem, maybe we would also get some insight how to understand from properties of the link, global properties of the hypergraph. And that's why I think it's an interesting problem in its own, even though it's not completely related with the subject of my talk. Anyway, there's a second construction which I want to briefly mention, which goes back to Erdős from the 80s, and it will be a weakly dense hypergraph without K43. Of course, we have just seen such a hypergraph, because if you don't contain a K43 minus, you cannot contain a K43. But this one has a feature that it's denser, so it will have density 1/2. And the construction is kind of similar. So again, we do something randomly on the pairs. So this is a very common feature of these constructions. So this time the vertex set will be ordered. So let's just say it's the first n natural numbers, 1 to n. And we color the pairs randomly red and blue. And now we include a triple if the two pairs incident to the first vertex have different colors. So another way to say is that we kind of order the vertices, and on the right link, kind of if I take a vertex and I want to decide on all triplets where this is the first vertex, then on the later vertices, I just put a random complete bipartite graph. This is the same construction as this one. And due to this, you can easily check it will be weakly dense with density 1/2. And it will not contain a K43 for a simple pigeonhole argument. So you just start. So imagine this is the first vertex, second, third, and fourth. So these two must be different in order for the first triple to be present. But then for the remaining pair, if you make it blue, you miss an edge. If you make it red, you miss a triplet. So you cannot have all four triplets cannot be present. Yeah, so let me mention that in both of these examples, we did something. So we, in the definition, we measure the density with respect to the vertex set. And in order to trick the hypergraph, we take some construction which heavily depends on the pairs. And this way we could forbid certain substructures, even though on the vertex level, the hypergraph looks fairly random, okay? And the existence of such constructions kind of are one of the main reasons why these hypergraph regularity lemmas developed by Gowers and Erdős et al. 15 years ago, they have to take the structure of pairs into account. And I would like to briefly mention a little bit about this method, because it was one of the key tools for the work of which we had together with Christian Reyer and Wojtek Röde on these extremal problems for uniformly dense hypergraphs. So let me briefly give some rough picture of how this hypergraph regularity method looks. Okay, so for that, again, we should start maybe with graphs. And basically what it says, the regularity lemma of Szemerédi, it says that any graph G can be decomposed. You can partition the vertices into some classes in such a way that most of the pairs, these bipartite induced graphs, which you see here, they have a kind of random-like structure. And in fact, they have this bidense property, which we defined a couple of minutes ago. But the densities may differ, right? And that's why I used here different shades of gray. Maybe darker shades mean denser bipartite graphs. But this is what this lemma basically tells us. And this is one of the kind of main tools in extremal graph theory. Now, in order to obtain similar strong lemmas for hypergraphs, which then allow you the embedding of any fixed hypergraph, kind of, you have, as we have learned from these examples, or I tried to convince you with these examples, you have to take the structure of the pairs into account. So you will have not only the hypergraph, you don't view it as a triplets and vertices, so you have some additional pair structure. And so in order to define it, you should think of it that, let's say you have a graph on the same vertex set. You look at the triangles, the set of triangles, and then you measure the hypergraph with respect to the triangles of the underlying graph, okay? And this defines maybe the density of H with respect to this particular yellow graph, or kind of triangles of this yellow graph. And now in this hypergraph regularity method, what you want that the density then stays the same for arbitrary subgraphs of the graph G. So you say H is regular not with respect to the graph G, if whenever I take a subgraph of G, I have on top of the triangles of G prime, I get the same proportion of triples as on the triangles of G itself. Okay, and if this is true for any subgraph of G, any subgraph G prime of G, then I would say the hypergraph is regular or quasi-random with respect to the graph G. And now what the hypergraph regularity lemma provides, instead of a partition of the vertices, roughly speaking, it gives you a partition of the pairs into graphs G1 to GL, so that H is typically regular whenever you take 3 of these graphs together and you look at the triangles which have one edge from each of the graphs. Okay, so this is the notion which comes up, and with this kind of notion you can prove stronger embedding lemmas, and you can kind of avoid these constructions earlier, or you can analyze them because you study how the hypergraph behaves with respect to pairs and not with respect to vertices only. Okay, so let me go back to these extremal problems. So what do we know about these Turan densities for weakly dense hypergraphs? So maybe one of the earlier papers besides this initial work in the 80s is due to Mubai and Rödel, who just showed that there's an example F for which this Turan density, this restricted one, is strictly smaller, right? We already know this monotonicity less or equal, but maybe it could be equal in general, but they showed there is an example where it's strictly smaller. And I already mentioned this result of Glebov, Kral, and Bolletz, which we reproved together with Raya and Rödel using hypergraph regularity method for this K43 minus result, that this Turan density, the density which we get from the tournament example, is optimal here. Moreover, kind of, so what are the basic things if you have such an extremal parameter? Maybe you want to know when it's 0, kind of getting an analog to the Erdős 64 result, which we have seen at the beginning of the talk. And we had developed such a characterization a couple of years ago. And from this characterization, it followed that the first non-zero value of these Turan densities is 1/27, or is at least 1/27. And Gabe, Kral, and Lamai-Zong showed that, in fact, there is also a hypergraph realizing this Turan density. In recent years, there were a couple more results, so people were studying it for so-called tight cycles. And maybe another kind of nice observation follows from the work of Balog, Kleiman, and Liditsky, that in fact, also for the clique on 4 vertices, this restricted Turan density is strictly smaller than the normal Turan density, which kind of was verified with computers by then. So what are the maybe main or urgent open questions in this area? So I think the nicest open problem is certainly, or in my opinion, is to determine it for K43. So we are a little bit better for this notion than for the traditional notion, at least for K43 minus it was resolved, but also for K43, maybe the second most natural question you can have, we are still a little bit stuck. And we have seen this construction, which gives a lower bound of 1/2. And yeah, I think it's kind of believed that this one is optimal in the sense of density. And yeah, so far this is open. More generally, this construction, just applying it with more colors, you can get a general lower bound for cliques on T vertices. And it would tell you that if these would be optimal, that then these Turan densities would behave like the normal Turan densities in the graph case, just a little bit shifted, right? In the graph case for a clique on 4 vertices, you get 2/3, you get 1/2. But for the clique on 5 vertices, you would get 2/3 and so on. And another question, which I kind of like, or it would be nice if one day one could answer such a question is it true that the Turan density for these weakly dense hypergraphs is always strictly smaller than the normal Turan density? If possible, of course. If the normal one is already 0, then this is impossible. But in all other cases, it could be. Right, in some sense, this relates to the first and last result, which you see up here. So the first result shows that it's at least one where this inequality is strict. And the last one verifies it, for example, for K43. But it could be that it's this inequality is strict in all cases. And the motivation for this question is a little bit the following, that all the constructions for the normal Turan problems we know, they either have somewhere a large set of vertices where there are no edges at all, so where the density is 0, which is kind of course, forbidden by this notion, because we could just take 3 times the same set for x, y, and z. Or there are these, I briefly mentioned, iterated construction, and for them it's also easy to check that they don't satisfy such a uniform density condition as defined earlier. So in case these are really the only constructions which exist for 3 uniform hypergraphs, then this would maybe give some indication that such an inequality could be true in all cases. But yeah, maybe it's false. But anyway, I think it would be interesting to answer such a question. Okay, so in the remaining time, I briefly want to tell you some other notions which you can, or which were studied and considered in the 3 uniform case of uniform density. And in particular, the first notion gives maybe a little bit more indication that this conjecture, the first one that you see here for the Turan density of K43, that this 1/2 could be optimal, because for a slightly stronger uniform density assumption, we could verify it. And let me briefly talk about this. So what we have seen before was weakly dense, and there we looked at the density induced by large subsets of vertices, x, y, and z. And now we change the picture and allow, instead of y and z, we take some finer control. We can take some arbitrary set of pairs. So in some sense, the way it relates to the one on top is here we always took the complete bipartite graph between y and z. And now why not taking an arbitrary graph, right? And in order to define this, so we consider a 3 uniform hypergraph H. We have a set of vertices x, and we have a set of pairs p. And we consider all triplets which contain a vertex from x and a pair from p. And we count it in an ordered way so that these parameters make sense. And so with this notion of density, we would now say that such a hypergraph is p-dense for this notion, where we use now this picture dot and edge, because we have a vertex set and a set of pairs. So the dot indicates the vertex set, the pair, the set of pairs p. And if for all such choices, we get always a p proportion of the triples in the same way as before, then we would say the hypergraph is p-dense for this notion, h dot p-dense. So here's a picture, maybe how to look at it. And as I already said, so this is a stronger notion, because if you just consider pairs p, which are the cross product of y and z, you immediately get the weakly dense notion from before. And for this notion, we showed that there the Turan density of the clique is indeed 1/2. And this is optimal because the construction, the Schroeder construction, which I showed you a couple minutes ago, kind of also satisfies this slightly stronger condition. So one can check that it's not only 1/2 dense with respect to vertices, but also with respect to one vertex set and one set of pairs. So that kind of maybe can be seen as a small indication that this conjecture for the just the Turan density in one vertex sets for K for 3 is also one. Anyhow, so if you are willing to consider such a notion with one edge, then of course you may consider what happens if I put here 2 edges and maybe in the end 3 edges. So if you put 3 edges just to kind of jump a little bit ahead, then you get the original, then you get this notion of the hypergraph regularity lemma, which I briefly discussed some time ago. And then you would embed everybody, and then you would get the analog of the graph result, because then the Turan densities would be all 0. So the only intermediate case in these type of pictures is if you put 2 edges. And so this is the last thing I would briefly like to talk about. And this notion you can define kind of in a similar way like this. So now you would take 2 set of pairs, P and Q, and you measure the density with respect to the cherries, which you can build with 1 edge from P and 1 edge from Q. But this is maybe nicer to describe it, or easier to describe it, is that this notion guarantees you this link property, which we discussed when we looked at the tournament example, that now you get the property that every vertex has a dense link, bidense link, as we defined it in the graph case at the beginning of the talk. Okay, so we will say a hypergraph is P cherry dense if, or let's say all or almost all vertices have the property that if you look at their link graphs, then this is bidense on its own. Okay, and this is equivalent to this PQ cherry notion, which I briefly mentioned a couple of minutes ago. And for those who like to think in terms of reduced hypergraphs after applying the hypergraph regularity lemma, it basically means a minimum co-degree, appropriate minimum co-degree condition in such object. Anyhow, so for this notion, together with Christian and Wojter, we got some general upper bound for cliques, but which are kind of familiar fractions, which you see here, as we have seen them already in the Erdős-Stone theorem and in Turan theorem. But now kind of it's for the cliques of size 2 to the t and not for the cliques of size t+1. So kind of this is this parameter grows much, much slower. Okay. And maybe somehow surprisingly at this time, and we proved this result, we had matching lower bound construction, which settles the case. I mean, for K43, you get here 0. And then for K8, you get 1/2, but there was a matching lower bound construction already working for K6. And for K16, you get 2/3, and we had a matching lower bound construction which works already for K11. Kind of, so we could settle the Turan densities for cliques of size up to size 16, except in the case 5, 9, and 10, which is maybe a little bit surprising because usually you think for larger cliques it should be more complicated. But yeah, so this is how it was. And somehow this is a little bit, I mean, usually you don't want to ask such a particular question, how is it for K9, how is it for K10, but somehow if you see such a picture, when you know everything between 4 and 16 and there are 3 gaps, somehow you feel the urge to work on these gaps. And that's precisely what we did. And for K53, so we, just to summarize what we had from this earlier result, we had a lower bound of 1/3, which was a construction, and the upper bound 1/2, which just follows because already for K8, it's at most 1/2. And yeah, recently we could settle this that the lower bound in this case is right. And it may maybe at this talk not surprise you that we use the hypergraph regularity method in order to prove that. And some careful analysis of sparser spots as kind of is maybe the typical theme in such arguments. And of course, this leaves open the case K9 and K10, as I said. So it's maybe sounds a little bit particular, but kind of, you know, everything between 4 and 16, except for 9 and 10. It's obvious that you have to work on them. And it would be very nice if this could be resolved. And I think with that, I finish my talk, and I thank you very much for your attention.
Thank you very much, Mathias. And since this is as live lecture as we can have, let me ask you, there was an odd result by Redl and Frankel and Redl that hypergraphs do not jump. If we add this weakly density conditions, then can we make hypergraphs to jump after all?
Yeah, so that would be one of the conjectures. So in the weakly dense, I would believe that they don't jump. That for this,
they still don't jump.
I mean, they prove that that they jump. Sorry, that they jump. So
already
the weakly dense notion, I would rather believe that they jump. That the spectrum is kind of like in the Turan densities in the graph case, and that there are no such non-jumping spots as in the normal triple system case.
And the jumps are associated to some chromatic number or something?
Well, it's more kind of from this. I mean, of course, if you don't know some other lower bound construction, you think the lower bound construction you come up with are the only ones, right? So in some sense, all the constructions we know is in some sense, you color the pairs and you allow certain patterns to be triplets and certain patterns you don't allow to be triplets. And you would have to maximize such a problem. But kind of, yeah, so we are not at that point to really kind of have such a detailed understanding of the problem.
Okay, so thank you very much, Mathias, for this wonderful talk. And we may have further discussion on Discord. So have a good afternoon, everybody. Bye-bye.